This is a demo of an actual project we did, which involves a municipal town hall that includes a library and a theatre. We will be investigating the traffic nearby affecting the library to determine the background noise level of the receivers in the library. Since being in the Mediterranean, the custom is to leave windows open during the summer period. We will then run open plan office calculations based on ISO 3382 Part 3 to determine the sound transmission index and improve it. We will then look at the theatre as an isolated entity, where we will run room acoustic calculations, since we have already done the acoustical study and have measured data. This is the only acoustic software where one can seamlessly carry out outdoor sound propagation, room acoustics and open plan office acoustics in one environment. We will be using Google Earth to locate our place. Launch Google Earth and type in your location. We then need to measure the distances in order to scale our image. We have already saved the image, but just for demonstration purposes, enable the ruler and measure horizontally and vertically the distances. Now save your image and launch OTL. Just a brief intro on using the mouse and shortcuts. The middle scroll button rotates the geometry, and by using the Control and middle scroll button at the same time will allow you to pan the geometry. To select an entity, click the left mouse button, and the right click allows for various additional options, which we will come across later in this presentation. In the Geometry Viewer, you will find the various toolbars and panels located on the top, left and right hand side, which again we're going to be seeing in further details in the demo. When you launch OTL, by default there is a 100 by 100 ground area which we will delete and redraw later. Let's import our Google image now using the Import Image tool and enter the dimensions we have previously saved the image in from Google Earth. This will maintain the scale factor for us. Click Zoom to fit your model so you can see the whole picture. To import DXFs and drawings, you can either import lines only, or you can also import a ready-made 3D model which has been created in another third-party software, such as SketchUp or AutoCAD. In this demo, we're going to show you both, so we can also demonstrate some of the CAD tools that we have. First, we'll import our lines outlining the municipal complex, and then we will import our ready-made theatre. Now we're going to draw our ground. First, make sure our Snap to Grid is disabled to be able to snap to the corners of the image. Using the Insert Ground tool, click on the first two edges of the image and drag to the end. The ground panel on the right will then open, allowing you to assign your ground type from the database. In order not to obstruct our image, we can make our ground transparent by selecting the ground and right-click and select Make Transparent. Next, we're going to create our library using the CAD tools. Enable the CAD tool menu, and then using the Create Surface on Existing Points, we will select the lines of the floors of the library. When you reach back to the first point, right-click, and this will finalize your surface. Now select the floor and extrude it to the roof height to create your room. When extruding, the new entity is normally grouped. So now we're going to right-click on it and ungroup the object to several walls. Let's select the roof and locate it in our object tree. This will automatically be highlighted for you. Right-click on the entity in the object tree and add it to a group and rename it Library Roof. This will help us identify our surfaces for later. We're also going to make our roof transparent so we can model inside the room. Let's also locate some other surfaces, such as the floor, and add them to a group and rename them. At this point, we will delete the walls that have the door and window, and we're going to redraw them again. We're going to select the rest of the walls and add them to a group. To multiple select surfaces, click on each surface whilst pressing the Control key. This will then allow us to group them together and find them all under one entity in the object tree. We'll do the same for the theatre roof and the reflectors, and you can also change the reflector colors by using the right-click feature. We will now draw our door using the Create Wall tool. Just click on the first 2 points of the door width and right-click to finalize your wall. Then drag your mouse to define the height. To create the surrounding wall, use the Create Surface on existing points. Now locate the door in the object tree and group it and rename it. We'll do the same for the window using the Insert Wall. But because the surrounding wall is irregular, we're going to create 2 surfaces using the Create Surface on existing points. Now let's skip to the next configuration. Just as a parenthesis, the Configuration Explorer is a very handy tool where you can create as many configurations or clones of configurations with variations to compare, rather than having to create separate projects. You can also import configurations from other projects. Here we have already grouped several surfaces and colored them for you. Before we proceed, we need to check the normals of the library. The normals are the reflected sides of the surface and only apply in room acoustics and open plan office, and they're not necessary for outdoor sound propagation. The theatre's normals are already corrected, so using the Show Hide Normals tool, or N for shortcut, will display the normals of the room. The normals should be pointing inwards and are highlighted by a red cone. The non-reflected sides appear as transparent when you're facing the wall directly. As you can see here, one surface on the Windows wall is non-reflective. So we need to correct the normals by right-clicking on the surface and select Flip Normals. The same applies for the door as well. Next, we're going to create the bookcases in the library. Using the Insert rectangle, click on the first 2 marked rectangle corners in the model and drag to the other end, and click once using the left click on your mouse. Extrude the rectangle surface using the Extrude tool and manually enter a height of 1.80 m and enter. We need to also check the normals of the bookcase since they need to be reflective in the room, otherwise we can yield wrong room acoustic calculations. To enable us to select easily a surface without having to ungroup it, we can use the Select by Surface tool, And then if we go into shaded mode, we can also see the lines representing each surface. Make sure we go back to Select by Object now to be able to clone our bookcase. First, we'll set our clone distances from the option panel on the left-hand side. We will assign 0 for X, -2 for Y, and 0 for Z. Now, right-click on the bookcase and select Clone Selected Item. Clone the bookcase 6 times. We will now select them all and ungroup them to assign different properties to the different sides. Note that you can actually only need to do this once for the first bookcase before cloning, and then just by cloning it, it will clone the exact parameters that you have chosen for the first bookcase. But we wanted to do this the long way around just to demonstrate the various options. Select the sides of the cases representing the books and group them, and do the same for the rest. We will now place a desk in the library using our ready-made layouts. First, we're going to move the editing plane, which is the grid, onto the library floor. Right-click on the floor and select Move Editing Plane, and click again on the floor to assign it as the new plane. A shortcut as well is just by pressing G and then click on the floor will also do the same. Select the long desk layout and place it at the end of the room. We are now going to rotate the desk. Enable the Rotate menu in the CAD tools and select Pick by Edge. Select the edge of the desk and specify a rotation angle of 90 degrees and click Rotate. You can move the desk using the arrows in the Rotate menu or using the arrows on your keyboard and just manually entering the move steps. Next, we're going to create the external walls of the municipal building. The beauty of OTL is that you don't have to create the walls. You can just extrude lines and your walls are created in a second. Let's select the walls below the library since they have a different height to the rest of the building. Using Ctrl and left click to multiple select lines, select the rest of the lines and then extrude them. Next, we're going to create the roof slab using the Create Surface on Existing Points and extrude it by 0.5 meter. Draw around the perimeter of the roof and right-click to finalize the surface. And do the same for the other slab. and make the roof transparent so we can see inside. Let's insert our line source now. Select the Insert Line Source tool and click to begin your line source. A blue line will appear to show the start and end of the line. Click to end the line source and a window will appear where you can divide your sources either by angle or distance. Specify a distance of 15 meters between the sources and specify the start and end height of 0.05 being the height of the tires according to the Knossos database. Line sources are grouped as one entity, where you can assign the parameters just in one go. Double-click on the source line to open the source panel and choose the 3D representation of a car. Note that the 3D representation is only for presentation purposes, and we still need to assign the source spectrum, which we will do a little bit later. In the library, we're going to assign 4 receivers where we have some markers already there for you, and we will also place another source. Click on Insert Receiver and click on the markers to insert, making sure that your Snap to Grid is still disabled. Now select the Insert Noise Source and insert it on the far end where the marker is showing. We will assign a 3D representation of a man, and we can select the source spectrum from the database as average male or female speech. We will also disable the source from our calculations for the time being and enable it later when we run OpenPlan Office calculations. To import our noise source spectrum, go to Database, Project Sources, and create a new category, calling it Suite Project. Under this category, we will add our source. A new window will open where you can select to either import from a CSV file or from clipboard. You can import your source spectrum directly from a file or copy and import it from clipboard. Make sure that in both cases the cells are in 2 columns, the first displaying the frequency band values and the second the level values. Name your source and click Save. We now still need to assign the source spectrum, so back into the Geometry viewer, double-click again on the sources and select the newly added category and find the source. We will also draw a road, but we're going to disable this surface from the calculations. We will just create it for aesthetic purposes since we already have a ground. Just as another tip, you can convert any wall to ground if you wish by right-clicking and selecting Convert Walls to Ground and vice versa. Next, we will need to open our window to calculate the background noise level for the receivers. Select the window and enable the Rotate menu. Select Pick Edge and select the bottom edge of the window, and specify 45-degree angle and rotate. As we did with the road, we're also going to create some columns for aesthetical reasons, but we will disable them from our calculations. In this configuration, we have already created the columns for you, but we will demonstrate how to do this briefly using our Insert Cylinder tool. Select the cylinder tool in CAD Tools and click once. It will then enable you to manually specify the radius that you wish. Manually enter the radius and press Enter. It will then automatically allow you to define the height. Again, type the height definition manually and press Enter. Next, we will create some materials to use in our project. Go to Database, Project, Material Properties, and create a new category and name it Suite Project. Now create a new material in that category using the one porous parameter model and specify flow resistivity of 200,000. Call it Library Carpet and save. Next, we will create our structures. Again, go to Database, Project, Multi-layered Structures. Here we have already created some structures that we will be using for this project, but we will demonstrate how to use the multi-layered structure builder. Create a new category and call it Library Layers. Add a new structure in the category. The Structure Builder window now will open. Let's start our structure with 3 mm of air and find the new library carpet material we have just added, and add 11 mm of the carpet. To add a material, just double-click on it from the list or drag and drop. To assign the thickness, just double-click on the added material and change the thickness and color. On the right, you can see the impedance, absorption coefficients, and transmission loss of the structure. Name your structure and save it. Now let's add another structure for the library ceiling. First, we're going to create a new material which can also be added directly from the structure builder, and we're going to select perforated material this time. Specify a perforation rate of 50% and a radius of 4 mm. Name it Ceiling Perforated Panel and save, but don't add the material just yet. We will start our structure with 400 mm of air and 50 mm of glass wool, which can be found under the 6-parameter model. Now add 12.5 mm of the new ceiling perforated panel that we have just created. Switch to the absorption coefficients graph. To demonstrate the scattering effects at high frequency bands, we can add 5 mm of absorbing material at the end. If you toggle between the able and disable tick under the material, you can see the difference in the graph. Save your structure. And now we're going to create a glass structure for the library window. Under Plate, select Glass and add 2 layers 3 mm each of glass. Add 18 mm of air between them and another 2 layers of glass with 4 mm thickness each this time. Save the structure as Library Window Open. We now need to go back and assign the materials in our model. In the object tree, find the library floor, ceiling and window, and in the wall panel select the new category and the newly added materials that we have just created. Now that we have completed the library, where our next step is to run the outdoor sound propagation calculations to determine the receiver criteria inside the library. In case you already have a noise criteria rating you wish to use, you can, by the way, select the curve from the database in the receiver panel. You can assign the criteria to multiple receivers by selecting them manually while pressing Ctrl, or selecting them collectively from the object tree. In the calculations options, we will specify 2 orders of reflections and 1 order of diffractions, and 2 orders of reflections between diffraction points. We will calculate the top 1000 paths per receiver, and we'll specify path length of 300 meters. Under the Calculation tab, we will select our sources to be incoherent, and we will use the finite impedance and spherical wave reflection coefficients with atmospheric absorption. You also have the option to show all the paths before running a calculation. Just press the Show All Paths button, and the top strongest path will be displayed between each source and receiver. In the Path Explorer, you can see each path's contribution, and by selecting a particular path either in the Geometry Viewer or in the table, the corresponding path will be highlighted. Now let's run our precise calculations. In OTL, we have indicative and precise calculations for each module: outdoor, room acoustics, and open plan office. Indicative calculations are fast and are an estimation, and the precise are the accurate calculations. In the results graph panel, you can see the precise calculation results in octave bands. The graph shows the assigned noise criteria, the level before and after, and any excess noise levels. Results can also be seen in a table and can be selected and copied to use in another third-party software. There's also an LED meter on the right-hand side, just indicating whether you are within or exceeding your limits. At the same time, the results are also displayed in the output window in octave, third octave, and high resolution curves. We're now going to select the level before or after, since they are the same for this particular calculation because there are no barriers or remedial walls for the moment. And we're going to export the octave boards to clipboard. In our database project criteria, we have now created a category with the receiver criteria, but we're going to demonstrate how to do this manually. Create a new category, call it Receiver Criteria Background Noise Level, and add a new criteria under the category. Select Import from Clipboard. Name your criteria Receiver 1 and save, and do the same for the others. We now need to assign the criteria to our receivers. In the Geometry Viewer, select each receiver from the object tree. And note that whenever you select an entity in the object tree, it will zoom to that entity in the Geometry Viewer. And from the drop-down menu, select the added criteria. Even though we will not be needing a barrier for this project, we're going to quickly demonstrate how to create one. Enable the Snap to Grid, and you can set the grid sizes in the Option menu. Select the Insert Barrier tool. Click on the first point to start your barrier and the last point to end it. The height definition will then be enabled, and you can enter the height manually. In the barrier panel, you can select the materials and adjust the dimensions. You can also change the barrier type either by selecting it from the drop-down option or just by right-clicking on the barrier itself and selecting one of the options. We're now ready to run our open plan office calculations. But first we need to close our window. We will also deactivate our line source since they're not going to be needed and activate our source in the library. If you are more familiar working with absorption coefficients rather than flow resistivity, there is a conversion tool available. Just click on the surface you wish to assign the absorption coefficients to. Now click the Convert to Absorption Coefficients tab and make sure that the selected checkbox is enabled. We have placed a laminated glass partition on the desk in the library and set it to Remedial. In the Calculations options, we specified 500 images to trace, as we don't need more than that for this project, and to calculate the top 20 strongest paths. We have defined one order of diffractions and one order of reflections between diffraction points. Before we run the calculations, we're going to run indicative, the estimated, room acoustics calculations to see the reverberation time in the room. The indicative results can be seen in the results graph panel, displaying the Sabine and airing curves. We won't run the indicative calculation for office since we need the precise calculations. Run the open plan office calculations. You will then see the paths displayed between the source and receivers. The calculation results will appear in the output window under the Open Plan Office tab. Briefly, the graph on the left shows sound transmission index. Anything above the blue line indicates that speech is intelligible. Anything below the blue line indicates that speech can be heard but is non-intelligible. Anything below the orange line indicates that you can hear somebody talking, but you're not being distracted from your activities. On the right-hand side shows the rate by which the speech drops with distance. It also shows the background noise level of each receiver. If the background noise level is higher than the speech level at the receiver, it's most likely that there is better privacy. Every time you press Calculate, there are two calculations taking place. One taking into consideration the presence of the remedial wall and one without. So by enabling the before and after, one can compare and see the effects with and without. Results can also be seen in the table below. Let's move on to our room acoustics calculations for the theatre. We assume the theatre is well insulated and not affected, and therefore will be carrying out room acoustic calculations as an isolated entity. In the next upgrade of OTL, we'll also be including building acoustics, which will allow us to also investigate sound transmission between spaces. We have made the walls transparent just to be able to see what's happening inside. We have assigned the average absorption coefficients calculated based on sound measurements to all the materials in the theatre. In the calculation options, we will specify 5,000 images to trace and calculate the top 100 paths. These are the paths that are going to be calculated for the impulse response and for the sound transmission index in the theatre. We need to use at least one order of diffraction on the model and walls and two orders of reflections between diffractions. We specify the path length to be approximately half of the measured RT in the theatre. Now let's run the room acoustics calculations. In the output window, we can see the impulse response of the room under the Time Domain tab. To zoom in, just drag the mouse over the area you wish to zoom into. Results can also be exported to a CSV or clipboard for post-processing and other third-party software should you wish to do so. In the Room Acoustics tab, you can select to see the various parameters such as the Sabine, airing, T30, T60, and so on. You can also specify your RT criteria. You can see the sound transmission index in the room as well as the clarity and strength. We're now going to do a mapping inside the theatre. Since the audience area is sloped, we will first adjust our editing plane, the grid in other words, to the seating area. Make sure the Snap to Grid is enabled in order to place our mapping area on the grid. Select a mapping tool and in the Mapping Area Picker window select Add. You can add as many areas as you like. You can select a surface to map on, or you can draw a rectangle for a specified area. In this case, we will draw a rectangle over the seating area which is snapped onto the editing plane that we have already specified. Click to start the rectangle and click again to end it. In the mapping window, you can increase or decrease the number of receivers in your area accordingly. We will rotate our area since it's inclined, so to do so, you can select either to rotate in the center or on one of the edges, which are labeled P1, P2, P3 and P4. For this mapping, we will rotate on the edge P4 and P1. You can also move your area using the arrows and step distances. Once you're ready, click Add. In the Mapping Area Picker window, make sure you select the Room Acoustics mapping area. If you are mapping for outdoors, then you would select either Precise or ISO 9613 Part 2 method or both. Select the receiver criteria for the sound transmission index and click Plot. Mapping results will be displayed in the output window under Mapping. You can select to see the different parameters. Let's select RT and change the interpolation points. You can choose to see the mapping with or without the geometry. By double-clicking on the mapping, you will be able to see the RT values at each receiver point. And you can also change the 3D plot heights. You can switch to 2D mapping, and you can also export the results to clipboard. To save various screenshots, you can right-click on your mapping, or a graph, or anywhere in your geometry viewer, and just select Copy the screenshot or save it for your reports. Now that we've completed the room acoustics calculations, let's move on to the sound distribution and scattering polar plotter. We're going to plot on a reflector in the theatre to see the sound distribution and scattering effects. Enable the polar plot from the Calculations menu, and in the Picker window select Add. You can either select by edge, points or coordinates. Let's select an edge and click on an edge of a reflector we wish to examine. You can move the area using the arrows and specify the radius, the start and end angles and the frequency band. If you wish to include the direct paths in the calculations, just enable the checkbox. Click Add and Plot. In the Output window, the results are displayed in the Polar Plot tab, where you can see the plot in a graph or in the geometry. By right-clicking on the axis on the left, you can view the calculation details and export your results to clipboard. This completes this demo project. We hope it has given you a clear overview of using OTL. If there are particular features you would like to see, please do let us know. Thank you.